Good day everyone. Welcome to our discussion in transmission media and antenna systems. Our topic is random wire antenna. Introduction, long wire end-fed wire antenna. The long wire antenna, more correctly end-fed wire antenna, consists of a length of wire as high and reasonably long as possible. It is one of the easiest antennas to make and erect. These antennas have been used for many years and provide a particularly adaptable form of antenna, especially for newcomers to radio communication. What is often loosely termed a long wire antenna simply consists of a longish length of wire that is connected to the transmitter or receiver, preferably via an antenna tuner. Strictly speaking, a long wire antenna is just that a very long piece of wire, many wavelengths long. However, the term is widely used to describe a random length of wire used to receive and often transmit signals on the high frequency or short wave bands. In reality, the term long wire antenna should be replaced with the term end-fed wire, unless if the antenna is many wavelengths long and a true long wire antenna. The end-fed wire antenna simply consists of a length of wire that is as high and reasonably long as possible. The wire is then connected to the transmitting and receiving radio communication station. The antenna wire is then typically taken out of the radio room or shack and taken to a horizontal section that runs above obstructions. Once the wire leaves the receiver, transmitter, or antenna tuner, the wire starts to act as an antenna, picking up signals and radiating them. For best receiving performance and also to ensure that when used with the transmitter, the correct impedance is seen, an antenna tuner or antenna tuning unit or ATU should always be used. The antenna tuner is placed between the transmitter or receiver and the antenna wire. If a tuner is not used, then the impedance of the antenna will not match that of the receiver or transmitter input, and this will result in lower efficiency. Also, the transmitter may have trouble matching to this, and this may result in lower power output or even damage to the transmitter output. A further requirement is that it is necessary to have a good radio earth. This is not the protective means earth, but an earth connection against which the long wire antenna or end-fed wire can work. The wire to the earth connection should be as short as possible, otherwise the inductance in the wire will start to place the station at a radio frequency potential above ground. So, random wire antennas. A so-called random wire antenna is an end-fed antenna as typically installed. It is a compromised antenna but great for portable use because it is easy to pack and easy to install. One end goes straight into the rig, often with no feed line, and the other end in the air attached to something as high as you can find. It is important to use a counterpoise. A standard recommendation is an 84-inch long end-fed and a 17 long counterpoise. While these lengths have been shown to work well on many bands, which is helpful if you're in a hurry to get on the air. A random wire is a radio antenna consisting of a long wire suspended above the ground, whose length does not bear a relation to the wavelength of the radio waves used, but is typically chosen more for convenience. The wire may be straight or it may be strung back and forth between trees or walls just to get enough wire into the air. Such antennas are usually not as effective as antennas whose length is adjusted to resonate at the wavelength to be used. Random wire antennas are a type of monopole antenna, and the other side of the receiver or transmitter antenna terminal must be connected to an earth ground. They are widely used as receiving antennas on the long wave, medium wave, and short wave bands, as well as transmitting antennas on these bands for small outdoor, temporary or emergency transmitting stations, as well as in situations where more permanent antennas cannot be installed. Often, random wire antennas are also inaccurately referred to as long wire antenna. Long wire antennas require a length greater than a quarter wavelength of the radio or half of the radio waves. Most consider a true long wire to be at least one wavelength, whereas random wire antennas have no such constraint. However, problems can occur when the length of the so-called random wire happens to be a multiple of half wavelengths of the transmitting frequency. Odd multiples of the quarter wavelength do not have this problem. This reduces the efficiency of the antenna and should be avoided. For the amateur radio high-frequency bands, operator WOIPL developed a table of a usable odd multiple lengths and then down-selected this to pick an ideal work any band length of 74 feet. So, radiation pattern. The radiation pattern of a straight random wire antenna is unpredictable and depends on its electrical length. Its length measured in wavelengths of the radio waves used. The radiation will drop off to zero on the axis. However, it may have several lobes, maxima at angles to the antenna axis. Under about 0.6 wavelength, our antenna will have a single lobe with a maximum at right angles to the axis. Above this, the lobe will split into two conical lobes with their maximum directed at equal angles to the wire and the null between them. This results in 4 azimuth angles at which the gain is maximum. As the length of wire in wavelengths increases, the number of lobes increases, and the maxima become increasingly sharp. The above applies to random wires in space. The presence of the good modifies the radiation pattern. A long wire antenna close to the ground will also act somewhat as a traveling wave antenna and have reception of the end of the wire. A folded or zigzag antenna will exhibit a pattern that is even more complicated and difficult to predict. Long wire antennas are reported to be more effective for reception than multi-element antennas such as Yagi or quad antennas with the same length of wire. So, construction. A random wire antenna usually consists of a long, at least 1/4 wavelength wire with one end connected to the radio and the other in free space, arranged in any way most convenient for space available. Ideally, it is a straight wire strung as high as possible between trees or buildings. The ends is insulated from supports with strained insulators. Typically, it is made from number 12 or 14 AWG, 1.6 to 2.0 mm, 0.063 to 0.079 inches diameter, copper clad wire. Folding the wire into a zigzag pattern to fit it in a limited space, such as an apartment or attic, will reduce effectiveness and make theoretical analysis extremely difficult. If used for transmitting, a random wire antenna usually will also require an antenna tuner, as it has an unpredictable impedance that varies with frequency. One side of the output of the tuner is connected directly to the antenna without a transmission line, the other to a good earth ground. A quarter wavelength size wire works best, and unless fed through an anode. A half wavelength will exceed the matching ability of most tuners. Even without a good earth, the antenna will also radiate, but it will do so by coupling capacitively to any nearby conducting material. This is not recommended. The ground for a random wire antenna may be chosen by experimentation. Grounds could be returned to a nearby cold water pipe or a wire approximately 1/4 wavelength long, or can be replaced by randomly laid out quarter wavelength counterpoise wires attached to the ground connection. This is a typical permanent wire antenna wire antenna strung between two buildings. This example has a lightning switch to ground the antenna for safety during electrical storms. So next, how long the wire or random wire antenna works. How the long wire or random wire antenna works. The antenna element works the same as any other antenna. Electromagnetic radiation comes from current flowing over spatial distance along wire. The single wire feeder not only radiates electromagnetic energy, it has very strong electric and magnetic induction or energy storage fields surrounding the wire for some distance out from the wire. In order to force current up into the feed wire and antenna, the matching or feed system has to push against something else. For every milliampere of current flowing into the feed wire of the long wire antenna, an exactly equal current has to flow into a ground system of some type. In any non-terminated antenna, currents and voltages are transferred along the antenna. This transformation is caused by standing waves. This means ground leads currents can increase or decrease along the ground wire and everything connected to the ground wire or ground system. Voltage changes also along the ground or counterpoise system, just as it does in antennas. The voltage caused by antenna return currents and the return current will become stronger, more intense, or weaker, less intense because of standing waves on wiring and equipment cases. These ground currents, displacement currents, or common mode currents cause everything connected to the matching system to become hot with radio frequency. The result is generally all sorts of RF interference to active devices or even physical harm to the operator, such as actual burns, or on lower bands like 160 meters. Electrical shocks. These unwanted but very unnecessary currents ideally should flow through the lowest impedance path and widest area path we can manage. Noise from long-wire antennas. Radiation and field surrounding the single-wire feed system not only leak out. Unwanted noise and signals can also leak in. Radiation from the feeder and everything connected to the matching type, as well as common mode currents, also allows common mode noise ingress. This deteriorates receiving system noise performance. Common mode currents and induction field coupling also decreases transmitting efficiency. This effect adds unnecessary loss to the system. If things are just right, like having a fairly good RF or ground in the shock and power is fairly low, we can often get away with having a random wire or long wire brought directly into the shock, but that is more a matter of good fortune than good planning. Curing RFI and reducing noise and optimizing performance with single wire feeds. Repeating and expanding on what was said above, radiation and field surrounding the single wire feed system not only leak out, unwanted noise and signals can also leak in. This is an unsolvable problem with a single wire feed. The very best we can do is to relocate these problems to an area where they cause no noticeable problems. We can do this by relocating the feed point. Relocating the feed point can move strong magnetic and electric fields away from the operating position, house, wiring, consumer devices, and our sensitive equipment. This reduces noise into the antenna feed system and RFI caused by the antenna feed system. Method 1, which is the grounding. Ground rods have limited effectiveness except perhaps on very low frequencies. This is not saying we should not have ground rods, but rather depending on them for RF grounds is not a good idea. The RF ground should if possible contain radials of counterpoise wires and not just ground rods. Ground rods do very little good for RF. As a matter of fact, adding ground rods can decrease RF efficiency when an insulated counterpoise is used. With fairly low power and good luck, one way to mitigate noticeable problems is a ground plane at room level. This ground system can be as simple as strips of foil laid under a carpet. These conductive wide strips of foil would then be connected back to a wide station equipment ground bus. Stained glass hobby suppliers sell adhesive back copper foil that works very well and is easily soldered. Another choice is aluminum foil, but this requires pressure connections that tend to be less reliable over time. As an alternative to copper foil strips, a metal screen or grid of wires at floor level can be used. This system can be right under the carpet or can even be directly below the floor. It is important whatever is used, that is, have a low impedance RF connection to the cabinets or chassis of desk equipment. This type of counterpoise system makes the entire room, including the operator, rise in voltage and match the equipment chassis voltages. It also disperses or spreads the current and voltage around, reducing intensity of localized electric and magnetic fields. This is very effective for a second floor or higher story RF ground, like standing on a metal plate carrying high currents. There is a little potential difference between different areas of the high conductivity counterpoise. The antenna led from the tuner long wire terminal to the antenna should parallel and be reasonably close to the outside ground lead if possible. This forms a two-wire transmission line which helps to reduce external fields. The single-wire feeder should be kept away from the operator and RF-sensitive equipment. The lead to the long wire antenna should be as short and directly as reasonably possible because the feed wire is a leaky transmission line. The method 2, keep problems outside. The best method of taming a long wire is to install a good loss current or choke balloon just outside the operating room. This effectively puts distance between the leaky feeder and radiating ground leads outside and away from the sensitive equipment. This is the basic and simple system. A system like this is ideal for a minimal investment and unobtrusive counterpoise. Improving the system above. At the expense of simplicity, a better ground will improve efficiency. A better ground would be multiple radials or multiple counterpoise wires, the ideal system in which efficiency would nearly equal that of a balanced center-fed system would be a ground system similar to radials for a vertical. The ground system can include existing wire fences or metal plumbing, or might be a totally new system installed just for the antenna. A good enough ground system or large area counterpoise system reduces RF voltage on the ground terminal. If the voltage on the counterpoise or radial ground system is large enough to present a low impedance, station equipment in the antenna ground systems can be tied together. Isolation such as a current balloon might not be required. The counterpoise in effect becomes less hot with RF voltage. One common misconception is a near-perfect ground needs 120 quarter wave or half wave radials. This is not true. Even 15 to 20 radials can form a very lost ground. All we can do is install the best ground we can manage. The more wires used in counterpoise or ground and the more spread out the conductors are, the less critical and frequency sensitive the system becomes. The point of diminishing returns is generally around 15 to 25 radials. If 40 to 60 reasonably long radials are used, any further increase becomes meaningless. A semicircle of 10 to 20 radials dating outward from the feed point, generally following the antenna direction, is usually good enough to make further work a waste of time. The best systems would center equally on each side of the antenna. If possible, small systems should be suspended above ground, if possible, to minimize losses. So, advantages and disadvantages. Advantages of random wire antenna: no heavy expensive coaxial feed line hanging from the span. Very simple to install and construct, excellent stealth antennas, and inexpensive. Disadvantages are single wire feeder and ground lead radiate. Can be a problem for lightning. Single wire feed line can be burned or shock hazard. Require a tuner or matching system. So, this is the summary of our lecture. And I prepare 5 multiple choice questions. So that's all. Thank you.